Hi everyone, I am Dr. Bharat from Department of Mechanical Engineering, Global Academy of Technology. I am glad to be with you today. In this session, we will be trying to understand the concepts of shape functions in beams, why the shape functions in the beams are called as Hermite shape functions, and how to obtain the shape functions in global and natural coordinates. So stay tuned with us. Here we go. Shape functions in finite element method are the polynomial equations that are used to interpolate the solution of an element based on the values obtained at the nodes. The equation shown here is the simple form of a shape function. In this equation, q of x represents a field variable over an element and small q represents the field variables or the unknowns at the nodes. The shape functions will relate the field variables over an element with the field variables at the nodes. In simpler terms, suppose if we know the values at the boundaries of an element, these shape functions are used to find the values within the boundaries of these elements. So in between the boundaries of elements, if you would like to know any value, the shape functions, also called as interpolation equations, will help by interpolating the known values which are obtained at the boundaries. We will now determine the shape functions of beam element in terms of global coordinate system. Consider a beam element of length L as shown in the figure. To describe the behavior of the beam element under loading, a cubic polynomial equation of the form v of x is equal to a naught plus a1x plus a2x square plus a3x cube is considered. By applying the boundary conditions, the coefficients a0, a1 and a2 and a3 are determined. The viewers are requested to go through the previous video session on stiffness matrix of beams to understand how the coefficients are determined by applying the boundary conditions. The coefficients obtained by applying the boundary conditions are a0 is equal to v1, a1 is equal to pi 1, a2 is equal to 3 by l square, v2 minus v1 minus 1 by l 2 pi 1 plus pi 2, and a3 is equal to 2 by l cube v1 minus v2 plus 1 by l square pi 1 plus pi 2. In this beam element, the boundary conditions which we have considered are: at node 1, the value of x is equal to 0 and the transverse displacement is v1. The slope is considered as pi 1 at node 1, and the boundary conditions at node 2 are: the x is equal to L, the transverse displacement is v2 and the slope is pi 2. Substituting the values of a0, a1, a2 and a3 in this equation, we will be getting the interpolation equation that can be used to determine the behavior of beam under loading conditions. This equation which you see on the screen is interpolation equation, and rearranging this equation in terms of v of x is equal to n1 v1 plus n2 pi 1 plus n3 v2 plus n4 pi 2 will give the equation in terms of shape functions. In this equation, the Q represents the field variables or the unknowns, V1 and V2 being the transverse displacements at the nodes 1 and 2, and pi1 and pi2 being the slopes at the nodes 1 and 2. The equation, after substituting this equation, this is the final form of the equation which we have got after substituting the coefficients in the previous equation. This equation is rearranged. V of x is equal to V1 plus pi x. Here the values are multiplied 3 by L square V2 into x square term minus 3 by L square V1 multiplied by the x square term minus 2 pi into 1 by L, that is what we have obtained here, plus pi 2 into 1 by L. Okay, since we have got minus into plus, this will be minus multiplied by x square plus 2 by L cube V1, and here we have got x cube minus 2 by L cube V2 into x cube. Similarly, this term has been multiplied here. We have got here. Further simplifying, we have taken the common terms with related to V1. We have got V1 and another V1. We have got minus 3 by L square into x square, and there is one more V1 term here, 2 by L cube x cube. All these terms V1 is common and V1 is taken common in these terms. Similarly, pi 1 is taken common from pi 1 x minus 2 by L pi 1 x square and 1 by L square pi 1 x cube. In all these three terms, the pi 1 is the common term, common element. Similarly, V2 is taken common from these elements, 3 by L square V2 x square and minus 2 by L cube V2 x cube. That is how we have got this term, third term, and the final term where pi 2 has been taken common, minus 1 by L pi 2 x square and 1 by L square pi 2 x cube. These are the terms from which pi 2 has been taken common. After taking these common elements, rearranging the terms once again, okay, this is the equation which we have obtained. Taking 1 by L cube common from this above equations. Here from this equation 1 by L cube has been taken common. Once 1 by L cube, instead of 1 we will be left with L cube. 3 by L square, instead of 3 by L square we have a L square at the denominator. It will be converted into L, and L cube, since 1 by L cube has been taken common, so the term left over will be 2x cube. Similarly, in the other case 1 by L cube has been taken from this term, so L cube will be multiplied with x. Instead of 2 by L we will be having 2 by L square term, because 1 by L cube has been taken common. Similarly here, instead of 1 by L square, L will be left over. The other equations which you can see here, instead of 3 by L square we will be left with 3L. Instead of 2 by L cube you will be having 2x cube, because 1 by L cube has been taken out as a common factor. Similarly, in this term, instead of minus 1 by L you have got minus L square, because 1 by L cube is taken as common in this case, as well as instead of 1 by L square you have left with L. This is the equation of the form N1 V1 plus N2 pi 1 plus N3 V2 plus N4 pi 2. So this equation is of the form V of x is equal to N1 V1 plus N2 pi 1 plus N3 V2 plus N4 pi 2, where N1 is nothing but the shape function, first shape function 1 by L cube multiplied by L cube minus 3x square L plus 2x cube. N2 equal to 1 by L cube x minus 2L square x square plus Lx cube. N3 is equal to 1 by L cube 3L x square minus 2x cube, and N4 is equal to 1 by L cube minus L square x square plus Lx cube. These are the shape functions in terms of global coordinate system. So once again, let us remind you that the global coordinate system will have the coefficients in terms of x. Let us understand these shape functions in detail. A close observation to these shape functions reveal that each and every shape function are cubic equations, which are defined are represented by four parameters: v1, pi1, v2 and pi2. Mathematically, these cubic polynomials are also known as Hermite functions. This is one of the reasons why the shape functions in beam elements are also called as Hermite shape functions, and these shape functions are denoted by H. Let us still further understand what exactly the shape functions and how the shape functions will be defining the behavior of the beam under various loading conditions. As you see in the screen, the shape functions n1 can also be represented in terms of h1, and similarly n2 or h2, n3 or h3, n4 or h4. The shape function h1 is associated with v1 in this equation. If you can observe, the n1 is associated with v1, and v1 is available only at node 1. Hence, the value of h1 will be 1 at node 1, and since there is no transverse displacement v1 at node 2, the value of h1 will be 0 at node 2. Similarly, shape function h3. Let us understand how the shape function h3 is varied over the structure. The shape function h3 is associated with the term v2. n3 is associated with the term v2. And since there is no v2 term at the node 1, the value of h3 will be 0 at node 1, and the value of h3 will be 1 at node 2. Now let us understand what exactly the shape function n2 or h2 tries to explain us. The shape function n2 or h2 is associated with the term pi1. Now pi1 represents the slope, nothing but the first derivative of v1, and hence instead of h2, the first derivative of h2 will be equal to 1 at node 1, since pi1 exists only at node 1 and there will be no pi1 at node 2, and the value of the derivative, first derivative dh2 by dx, will be 0 at node 2. A similar analogous happens for shape function n4. It should be n4 here, the shape function n4 or h4. Shape function h4 is associated with the term pi2, which represents the slope or the first derivative of v2, and hence instead of taking h4 directly, we will be using dh4 by dx, which will be equal to 1 at node 2, because pi2 exists only at node 2, and the value of dh4, the first derivative of dh4 by dx, will be 0 at node 1. This is how the shape functions will be varying over an element. Now let us understand the shape functions. Let us derive the shape functions in terms of natural coordinate system. Before going into natural coordinate system, let us recap and understand how the shape functions are varying over the nodes. Once again, this structure, this figure shows a beam element with two nodes 1 and 2, V1 being the transverse displacement at node 1, V2 being the transverse displacement at node 2, pi 1 being the slope at node 1 and pi 2 be the slope at node 2. Here n1, the value of n1 will be 1 at node 1 because it is directly associated with V1. The value of n2, n3 and n4 will be 0 at node 1. Come back to node 2, the value of n1 will be 0, n2 also will be 0 because n3 is directly associated with V2. Now coming back to this first derivative, the slopes, the shape function n2 is related with pi 1. So the value, the first derivative dn2 by dx will be equal to 1, and coming back to this node 2, the value dn4 by dx will be equal to 1. That is how the shape functions are associated with the beam elements. Now let us derive the Hermite shape functions in terms of natural coordinates. Dear viewers and my dear students, this derivation is very much important for the examination point of view to the students, and the others can understand how the Hermite shape functions can be obtained in terms of natural coordinate system. The cubic interpolation polynomial equations that are used to interpolate the solution over the beam elements are called as Hermite shape functions, and these shape functions are denoted by h. In natural coordinates, the Hermite shape functions will be of the form h is equal to a plus b zeta plus c zeta square plus d zeta cube. Try to understand here. In natural coordinates, instead of x as a coordinate, we'll be using the value zeta. We'll be using the term zeta. Here the zeta always varies between -1 to +1. That is what the natural coordinate system. So the figure shown here represents a beam element in terms of natural coordinate system. H1, at each node there will be 4 shape functions, H1, H2, H3, H4, which represents the transverse displacements, and its first derivatives represents the slopes. Similarly, at node 2 we'll be having the terms H1, H2, H3 and H4 that represents the transverse displacements, and their first derivatives represent the slope at node 2. Using this as a boundary conditions, we will now derive the Hermite shape functions in terms of natural coordinates. To find the first shape function, let h1 is equal to a plus b zeta plus c zeta square plus d zeta cube. Let it be equation 1, and its first derivative being, since a is a constant, is missing here, and b zeta is zeta obviously will be missing here, it will be only b. C zeta square will become 2c zeta, and d zeta cube will be 3b zeta square. The boundary conditions, using these boundary conditions, we will try to find the values of the coefficients a, b, c and d. The boundary conditions at node 1 are the value of zeta is -1 at node 1, or because the value of zeta always varies from -1 to +1 at each node. So the value of zeta is -1 at node 1. H1 is 1 at node 1, and its first derivative is 0 at node 1. Substituting this boundary conditions in both the equations, will end up in equation 1a and equation 2a. 1 is equal to, since h1 is equal to 1, we are directly substituting 1 in place of h1, and a minus, instead of b zeta, zeta value is -1, so we have got -b here. plus C zeta square. So zeta square minus 1 whole square will be positive value, so we have got plus C, and D zeta cube, and minus 1 whole cube will be the negative value, so minus D. Similarly, the values this boundary conditions are substituted in equation number 2. Equation number 2 implies dh1 by d zeta whose value is 0. 0 is equal to B minus 2C because the value of zeta is minus 1 plus 3D where the value, this is D here, okay, the value zeta square, since zeta is equal to minus 1, the minus 1 whole square will be the positive value here. So once again, the boundary conditions at node 2. At node 2, the value of zeta is plus 1, the value of h1 is 0, as well as the value of dh1 by d zeta is also 0. Substituting these values in these equations, h1 as well as dh1 by d zeta, h1 is 0, so h1 we have substituted as 0. Instead of b zeta, zeta is plus 1, we have got the equation term a plus b plus c plus d, because the values of zeta is positive, is equal to plus 1. And equation 2, once we substitute equation 2 here, the first derivative is missing here in node 2. dh1 by d zeta value is 0, so 0 is equal to the positive value b plus 2c plus 3d. We have got 4 equations: equation 1a, 2a, 1b and 2b. Solving these 4 equations, we will be able to find the coefficients a, b, c and d. Now the coefficients obtained are a is equal to 1 by 2, b is equal to minus 3 by 4, c is equal to 0, d is equal to 1 by 4. Any advanced calculators nowadays can solve 4 simultaneous equations and you will be getting the values. Substituting these values in equation 1, we will be getting the equation of h1. On further simplifying the h1 shape function, we will end up in a shape function h1 is equal to 1 by 4 into 1 minus zeta whole square plus 2 in plus zeta. This simplification is further explained at the end of this session, and viewers are advised to practice the conversion from previous equation to next equation. This is how we will be finding the values of h1. Similarly, we will be trying to find the values of h2. This time we will be taking the equation h2 is equal to a plus b zeta plus c zeta square plus d zeta cube, this being d, and its first derivative dh2 by d zeta is equal to the derivative of the previous one. A close observation here, if you see, the right hand side of the equations has never changed, only the equations at the left hand side has changed here because of the boundary conditions. At node 1, the value of zeta is minus 1. Since it is minus 1, the right hand side equations is the same, and h2 value is 0. So the first equation, h2 value is 0, dh2 by d zeta is equal to 1. These are the boundary conditions. Applying these boundary conditions in equation 3 and 4. So equation 3, if you can observe here, instead of h2 we have got 0, and on the right hand side a minus b plus c minus d. And applying these boundary conditions to equation 4, since we have got dh2 by d zeta, in this place we have got 1. dh2 by d zeta is equal to 1, as well as h2 is equal to 0 at node 1. Now the boundary conditions at node 2, zeta is equal to plus 1 and the value of h2 is 0. You do not have h2 here, and the first derivative of H2 is also 0. Since they are zeros, so here you can see applying this boundary conditions to equation 3 and 4, you will end up in zeros in the left hand side, and the right hand side remains same as the previous case, being a plus b plus c plus d and b plus 2c plus 3d. We have got once again a fourth set of equations. By using this fourth set of equations, the values of a, b, c and d can be determined. The value of a is equal to 1 by 4, b is equal to minus 1 by 4, c is equal to minus 1 by 4 and d is equal to 1 by 4. Substituting these values in equation 3, H2 will end up in getting the shape function in terms of natural coordinates H2, whose equation will be of the form 1 by 4 plus 1 by 4 zeta plus 1 by 4 zeta square plus 1 by 4 zeta cube. Sorry viewers, here it should be minus, it is not plus, it should be minus because b is minus here, so the value should be minus. Make a note of this, b is minus, and the value of c is also minus here, value of c is minus, and d is equal to plus 1 by 4 zeta cube. This equation can be used and further simplified to get the equation H2 is equal to 1 by 4 1 minus zeta whole square multiplied by 1 plus zeta. This simplification is once again explained at the end of this session. Similarly, to find the equation for H3 is equal to a plus b zeta plus c zeta square plus d zeta cube, and the first derivative being b plus 2c zeta plus 3d zeta square. Applying the boundary conditions at node 1, zeta is equal to minus 1 and H3 at node 1 is 0. Its first derivative at node 1 is also 0. So applying these boundary conditions to equation number 5 and equation number 6 gives two additional equations 5a and 6a. 0 is equal to a minus b plus c minus d and 0 is equal to b minus 2c plus 3d. Applying the boundary conditions at node 2. At node 2, the value of zeta is equal to plus 1. The value of H3 is 1. We have got shape function here, since H3 represents the transverse displacement V3. Since V2 is available at node 2, this value will be equal to 1 and its first derivative will be 0. So the equations 1 is equal to a plus b plus c plus d as well as 0 is equal to b plus 2c plus 3d. We have got once again the four equations. Further simplifying, solving these four equations will end up in giving the coefficient values. A is equal to 1 by 2, b is equal to 3 by 4, c is equal to 0 and d is equal to minus 1 by 4. Substituting these values in H3, we'll be having H3 is equal to 1 by 2 plus 3 by 4 zeta. Since the value of c is not available, c will not be here. Okay, c will not be here, so c term will not be available in H3. Instead of d, we'll be having minus 1 by 4 zeta cube. On further simplifying this equation, you will end up with H3 is equal to 1 by 4 1 plus zeta whole square multiplied by 2 minus zeta. And the last, H4. To find the values of H4, once again we will consider two equations, H4 th4 by d zeta. H4 will be equal to a plus b zeta plus c zeta square plus d zeta cube, and its first derivative being b plus 2c zeta plus 3d zeta square. We got the two equations, equation 7 as well as equation 8. Applying boundary conditions, at node 1 and node 2. At node 1, the value of zeta is equal to minus 1, and the value of h4 at node 1 is 0, and its first derivative is also 0 here. Applying these boundary conditions to equation 7 and equation 8 will end up in getting two new equations. 0 is equal to a minus b plus c minus d, as well as 0 is equal to b minus 2c plus 3d. Now once again I want you to understand the right hand side equations will remain same, and only the equations in the left hand side are varying. The right hand side equations are the same here. Similarly, applying boundary conditions at node 2, the value of zeta is equal to plus 1 at node 2, and h4 is 0 at node 2, and its first derivative, since it is associated with the slope, its first derivative is equal to 1. So we have got two more equations. Solving these four equations will end up in giving the values of a, b, c and d. Substituting these values in h4, we'll be having h4 is equal to minus 1 by 4 instead of a here, minus 1 by 4. Instead of b zeta, we have minus 1 by 4 zeta. Instead of c zeta square, we'll be having 1 by 4 zeta square. Instead of d zeta cube, we'll be having 1 by 4 zeta cube. On further simplifying these equations, we will end up in h4 is equal to 1 by 4 multiplied by 1 plus zeta whole square and zeta minus 1. These are the four shape functions which has been obtained. So let us understand the variations of the shape functions over a element. The first shape function h1 is equal to 1 by 4 1 minus zeta whole square 2 plus zeta. This shape function represents the transverse displacement at node 1, and it will be varying at 1. h1 will be equal to 1, and from node 1 to node 2 it will be varying from 1 to 0. Similarly, if you observe h3 also represents transverse displacement at node 2. So the value of h3 will be 1. So it starts from 0 at node 1 and gradually moves towards 1. In both the cases, the slope will never represent the slopes. But when we come to the values of h2 as well as h4, this h2 and this h4 represents the slope, derivative or the tangent function. So h2 and h4 gives the slope at node 1, h2 gives the slope at node 1, and h4 gives the slope at node 4. This is how these functions will ensure that the beam can get a shape when it is loaded. The shapes can be clearly, the behavior of the beams can be clearly explained, determined by these shape functions. This derivation is very much important, and the Hermite shape functions always varies from 1 to 0 depending on the type of node, and the four shape functions which will be using beam elements h1, h2, h3 and h4 are called as Hermite shape functions. These shape functions are used to interpolate the values, the solutions between the elements. So let us understand how we have obtained, simplified the equations. This the viewers can just go through these equations. Okay, the process of converting the simplifying equations of one form to other form. Okay, you can just go through it. h1 is shown here, as well as the simplification process of h2 is shown. Similarly, the simplification process here, you need to ensure it is minus, it is not plus here, because the value of a is 1 by 4, b is minus 1 by 4, and c is also minus 1 by 4. It is not plus, minus 1 by 4. So these equations are converted. So obviously you can see that we have got minus here and also minus here. These equations, the simplification process is shown here. The equations for h3 and H4 are simplified to this form. This is only the simplification process is only for your understanding, but if at all you are trying to represent this in the external examinations, you can directly end up with this equations. Without this simplification, you can further continue with this Hermite shape functions. And that's all for the day. In the next session, we'll start with what are the different types of loads in the beams, what are the boundary conditions, what will be the effect of point loads, effect of uniformly distributed loads, uniformly varying loads on the beam elements, and in solving the numerical problems. And once again, viewers, thank you for watching this session. Hope you are practicing it. If you have any queries, you can mail me in this mail bharat.vk@gat.ac.in. Thank you.